Hello people, welcome back to my channel. So hope you are enjoying the Python skill series so far. So today what we'll be doing is we'll build a machine learning model. Basically it will be a linear regression model. So we have seen about the conceptual videos on different machine learning models like logistic regression, linear regression, SVM, neural networks, and many other. So I thought of let's discuss or let's construct a machine learning model with the help of Python knowledge, whatever we have gained so far, and some of the other coding techniques and also some of the other features that we have not explored so far with data frames or with other kind of libraries. So this particular video will be not only a revision of all the concepts that we have learned so far, but addition to some of the coding techniques, and it will give you a gentle idea of how to create your first linear regression model. Okay, so for this particular task, we again need a data set. So this data set I have taken from the UCI repository, which is cited on the Kaggle website. So I will again just cite that particular link in my video description. You may download from that particular link. So I have my data set loaded, that is auto CSV. And before that, let's have a small overview of how my dataset looks like or what this auto CSV is. So this auto CSV or auto 85, that is this particular data is collected from the year 1985. So in that particular year, what kind of automobiles were there along the streets, or what people used to drive in that particular time period. Based upon that, we have certain data. So this particular is the data set. So obvious thing which you can first notice is that there are no columns in this particular data set, and there are around 16 to 20 different columns which you can see. So to analyze in the first place for this kind of data which does not give you any metadata information. Metadata means what these columns basically represent. So if I just give you 332110 or something like this, and see in the other column you have question mark as well. So what this basically means. So for to analyze this or to construct any linear regression model or any model, first you need to have a domain expertise in this field who can give you pretty well understanding of what this columns and each and every entry is. So assume like I have did that activity from a domain expertise, and I have the knowledge of what the columns are. And so now primary task is to just rename these columns in my data frame. Okay, so first what we do is let us just import this data set, and for that I'm using the pandas, and to do some numeric operations I have the numpy. And then by this I'm just reading my CSV, that is auto CSV, and this is the syntax for rename the columns. We have seen this before in my pandas video. So the first column that is there, that is this one, that is nothing but symboling. So symboling, to give you a brief idea of what this particular column is. So this characterizes the risk factor, that is this number. So there is a particular range that is 0 to that is, it ranges from -1 to any higher number. Here we have up till 3. So what this basically gives is, it gives you the information collected by the driving style of that particular driver or the user, whoever is driving that particular car. So with all this particular cars, you basically have different kinds of sensors attached with it. So this sensors will collect n number of different data from the surrounding. It will capture the user information, what is the mileage, how many distance he has covered, and so all those things. So that is basically characterized by this symboling. So it is basically just an number which has values from -1 up till any higher extent. Then the second column which you can find is that is the normalized losses. That is another column that I get from the domain expertise. Then I have make. So make is the the automobile company. So you have Audi, then BMW, Chevrolet, Mazda, Mitsubishi, Mercedes-Benz, Nissan, Peugeot, Porsche, and so on. So that is the make. Then you have the fuel type. That particular automobile, whether it runs on gas or diesel or any other. So that is basically this fuel type. Then you have aspiration. Then you have the number of doors. Then body style. Then the drive wheels, engine location, wheelbase, length, width, height, curb weight, weight, engine, engine type, number of cylinders. Then again, we have the engine size. This is the engine type, and then we have engine size, fuel system, bore, stroke, compression ratio. HP stands for horsepower. Then the peak RPM, then city miles per gallon, highway miles per gallon, and finally the price. So price being our final column in this data set, so that obviously will be our target variable, that is our predictor variable. So given different features or different columns or different attributes for this particular data, our main objective is to predict the price of a given car. So that is the main objective of this particular model that we are going to create. Okay, so before we begin our activity, first we need to drop some columns or drop some entries which does not have any missing values. So else our regression model that we create will be meaningless. So for that I just run a df dot drop na, and I'll just summarize the different columns that I have created before. So this many columns we have. Now I'll just list out the data types that are available so far in this. So first we have symboling, which is of integer 64, then the wheelbase, length, width, height, curb weight, and many of the things which you can see. So you cannot make out like any of the objects that are of the object data type. Everything is converted to integer 64 and float 64. So we don't want to do any further pre-processing. So that will also see how we can do if it was not explicitly there. So we'll do that kind of activity also. And if you just observe into columns like say the fuel type, say here we have gas. So in this particular column, there are just two entries, that is either gas or diesel. But moreover, the distribution is moreover to the gas. So the type of fuel is moreover gas. So by domain knowledge or when I consult with the expertise, I get to know that this particular column will not be helpful for my analysis, and so my linear regression model will be severely affected by this particular kind of column if I take into consideration. And so with my expertise knowledge, I have got to know that some of the columns like make, then the fuel type, then engine location, then the number of doors, body style, drive wheels, engine type, and fuel system, aspiration, normalized losses, does not contribute much to my prediction. So this kind of variables I just don't want to consider to my linear regression model, else it will give some kind of other statistics or some kind of other insights which is not quite useful. So what I basically do is I'll just drop these particular columns from my data frame so that our model construction becomes much easier. Also, these columns which does not contribute much to your model, are considered as low variance filters. So which will cause any or a particular kind of lower accuracy to your model. So I basically go ahead and run this particular cell, uh, make not found on axis. Okay, so let me just do this again. And okay, now here it's seen. We'll just do this. So here we can see there are few objects that because of some activity it was just trimmed off. So now we can see there are few objects and few float data types that are visible. Now if I just run this, I can see like the columns that I've mentioned here. To drop those columns or those particular attributes are not there, and now we are only left with 16 columns. So now let's move ahead, and what we do is, if we again inspect this particular data frame, we have one column that is the number of cylinders that is in this particular column has values which are there in categorical. So one important thing that to note whenever you create any machine learning model or a deep learning model, these models will not work on object data types, means string data types. So it has to be either converted to float or integer values, whichever is more preferable. So I'll just go ahead and run this. So after we drop few of the columns, we have these many columns or attributes that is left for our analysis or model construction purpose. So if I just check for the value counts, I can observe like these many different columns are there in this, and these are the different counts. So now what I do is I'll do a conversion, or in fact a replacement to all of these values which are categorical in number. I'll just put a dictionary and I'll call the replace function, and in this what I pass is I'll just pass this particular label, that is originally what was it, that is here 2, and I will just represent the figure 2. So these are in words and these are in figures. So I do this for all the unique values that this particular column has got, and I'll just run this, and you can now see the column which is there here. So that is at the end. So the original number of columns that I have dropped in this particular activity, and the new column which I get, that is appended at the end of the data frame. Now you can see there are many other entries. So that is basically the missing value entries by the data analyst or the person who has done this data entry stuffs. So due to some missing values, or due to some macros activity, or due to some other integrity constraints which are there in the database while exporting, this may be converted to some values that are not interpretable. So basically our task now is to replace this question mark with some other measure. So what we here do is we replace all the question mark that is available in the data frame, not specific to one column, with np.nan. So np.nan is nothing but not a number. So we go ahead and run this, and we get this particular data frame that is now free of any question mark value. So now your data frame will not contain any question mark fields. Instead it will be replaced by nan. Now what comes is, uh, as you saw here, that is we just ran the df.d types. You can see there are few columns, that is this bore that is in object, stroke which is again in object, then horsepower which is again in object, peak rpm which is in object, even the price, that is an object. But when we just look at the data frame, that is the modified one, we can see those are in numbers, but internally it is storing in objects or strings. So we cannot do that, or that activity if we try to perform in our model, it will throw some error. So to handle that, we have to convert these object types into float type or integer type. So for that, what I'm doing is I'm just changing all the data types which were originally in numeric, but it was, or in the representation of the data frame, it shows as like the integers or floats. But internally, when we check the data types, those were not the same, or those were objects. So I'm just converting just to a standard data type, that is the majority in the data frame that we can see as float. So for that, I'm basically using as type, ASTYPE. So that is an inbuilt method which is present in the pandas library, and to that I'm passing float 64. So when I run this, it have internally converted to all the object to float. And if I just run this again, uh, you can see like all the object types that were there earlier have just converted to float types. Now what I want is the thing what I did here. So here what I did is, that is, we converted all the question mark values to nan values. So again, for nan values we have to do some treatment. So nan value is again a missing value. So with missing value, what we do is we replace the with the median value of that particular column. Now why with median value? We can also do with mean value. So median is because it's basically an aggregation function, and since all the columns contains numeric data, we can perform that activity. We don't replace with means because means are easily impacted by outliers. Now whenever we do any visualization, when we go down the line, we'll do certain plots. So in that plots we get certain distributions. So in these distributions, when you observe, this basically will be some Gaussian distributions. Ideally it should be Gaussian, but then we do the kernel density estimates. If you remember what KDE is, it will have severely impacted by noise or the outliers, so which we don't want to have, or which we try to keep it as minimal as possible. So what we basically do is, instead of replacing all the nan values with means, we replace with median values. So one peculiarity of median values is median values can be calculated for an object value also, but with mean that's not possible. But we will not take any further risk. Instead, we just keep it to the float values that we have converted in this particular step or in this particular cell. So I'll just go ahead and just run this. So now all the nan values which were there earlier, now it is being converted to the median values. Now I just do a df.describe, so that gives you a statistical overview of all the quantities that are required. So you can also put include is equal to all. So that gives you all the parameters, that is the count, standard deviation, minimum value 25th, the median value 50 percentile, 75 percentile, and max. So this minimum, maximum, 25 percentile, 50 percentile, and 75 percentile are called as the 5-point summary, which are a basis for any box plots that we do. So this is just a statistical evaluation. Now what we do is we go ahead and do the pair plots if everything is fine. So we basically import the cbond library and we do the pair plot, and pair plot is with a KDE, that is kernel density estimate. So just to make sure like everything works perfect, you have to do all of this pre-processing and treatment of the float data type, like which were the earlier objects. You have to do all of those activities, and also the nan value treatment you have to replace with median, especially because in this particular data frame, since all of the values are basically floating types, you can go with median value. Mean value, if you just do, or like if you just replace all the nan values with mean values, that would cause some other kind of representations, or you'll wrongly interpret your data. So to not to do all those kinds of mistakes, you basically can do with or replace with median values. So preferably median values are done, or all the nan values are replaced with median values for these data frames. And just make sure, like whenever you do the pre-processing, whether the column names are given or not. If column names are not given, you have to run this particular first cell, so that uh, you by default or with the domain expertise gives the column names, and it should be in accordance with the number of columns that should be there in all these entries. So that's why I always tell to make sure, like, you open the Google Sheets and just rename this. And I hope our pair plot is ready. Okay, so our pair plot is basically ready, and I'll just change this theme to light. Okay, and we can see along the diagonal that is each of the attribute with the attribute itself is a Gaussian, that is a kernel density estimate, and more the peak is. So if this peak is very sharp, that means you have a very little variance. So you can see most of the graphs. The first graph has a larger variance, that is symbolic versus symbolic, and this particular has a slightly lesser variance because it has a very huge peak. And similar is the case with length with length. Then you have the width, then you have the height, and then you have further other columns which are present. So this is the graphs or the pair plots, basically the scatter plot for bivariate analysis, because we have, or we are comparing amongst two different variables in the data column. So it will omit any categorical columns. Obviously we are not considering any categorical column in this. So for all the numeric columns we are doing the scatter plot. So what we do is we'll just do the analysis on some of the plots. So if I just zoom this, you can see that is this is symbolic versus this is the wheelbase. So since you have so many 16 different columns, that's why you get this plots, or this canvas is very small, or each of the plots are very small in appearance. Okay, so what we do is we just look at this, that is symbolic versus wheelbase. So if you just analyze this graph, so as the symbolic increases, the wheelbase value just goes on decreasing. And moreover, in each of the plots you have multiple values, because there are overlap of the data points that is observed, and there are some outliers which are also present at the very extremes. So it is due to the multiple values that is present, or also it can be due to the noise which is present while the data entry, because everything is derived from the data set. And with the wheelbase, with the third one, that is the length, which you can see here, it has a, positive relation, because this particular slope, that is an ideal case of linear regression, because for each value of wheelbase your length increases. So that is similar with the graphs in the further, but there you can see moreover, like some more no relations between wheelbase and with other parameters. If you just look at this particular graph, there are basically two different clusters that are formed in this particular scenario. So this is one particular cluster, and this is one particular cluster that may be due to some of the dimensionalities which it could not handle. So these are the some outliers or additional outliers which are present in your data set. And these are some of the visualizations which you can interpret. So if you just look at the compression ratio with the all other parameters, so this is for the compression ratio with all other 15 different columns or 15 different attributes, you can see there is a kind of grouping or clustering that is observed. So in everywhere you can see there are two kinds of clustering, and if you just see that is the compression ratio versus compression ratio at the tail of this Gaussian or the kernel density estimate, you can see that there are two peaks that is observed. So this small peak can be a sign of some kind of noise or unexplained variance which is there in your uh, data set. So that is characterized by this small peak towards the end. So ideally, the points which are earlier considered as outliers, now they are not being considered as outliers, or vice versa. You can draw similar kind of discussions over this. And moreover, this column treats in this way. And if we just go here, that is the cylinder converted, that is the thing which we have converted, that is from the words to all the numbers, uh, that thing. So that particular column with symboling, we can see like there is a range. So the cylinder converted has, or it had values 4, 6 and 8. So you can see there is a range of some particular cylinder conversion. So you have these many entries or these many instances that basically has 4 cylinders, and some has 5 cylinders, some has 6 cylinders, and some has 8 cylinders. But few or just one of them has 12 cylinders. So there are basically different kinds of ranges that is there. So which from your data set has some meaningful insight in your plot. So that is with the pair plots. Now what we do is we just do the blueprint or for training our model. So since I mentioned before, the price column that is at the very last of your data frame, that needs to be predicted given all this 14 different or 16 different columns that you have in hand. So I just take into variable x, and this is my column. Now it has only 15 columns. Earlier there were 16 different columns. Now we have just removed one column, that is the last column, price column. Now it's not there. And what we do is we instead take the price column in separate y, that is our target or predictor variable. So price needs to be predicted given all these different attributes or features are given. So that is just one column and 204 rows. This is 15 columns and 204 rows. So now what we do is we just call the sklearn model selection, and we just use the linear regression. So we are going to build a linear regression model because if you remember, it has of the form y is equal to mx plus c. So every independent variable will be dependent on two variables, that is the intercept and the slope. Slope in this case is nothing but your features, and whatever value it has, so we'll basically try to map a linear relation to it. So then we use the train test split method. So train test split method will take the training x and test of x. So this x what we have here, so that we basically divide into two categories, that is one in training set and one in test set. And similarly with the y, we also split that into training x and test x. So then this is the syntax of train test split. So to this we pass x, we pass y, and we mention what is my test set size. So I'm keeping my test set size as 25%. So my rest of the 75% goes to training set. So that is by default done by this particular train test split method. And then you have some random state. So random state is required because there should be some kind of randomness in order to handle by your model. Else in some places it may just bombard with some unmeaningful results. So in order to do that, you introduce a random state. In other models or classification models like in decision tree or neural networks, there also you have this random state parameter, and then you just invoke this class of linear regression and you just instantiate that. So this is nothing but the model instantiation, and you just put into a model variable and you just invoke the fit method, and to fit method you basically pass the train x and training of y. So basically on the training data which you have from both the predictor variables and the variables from which your data frame consists of, these two, you just basically train your linear regression model. So this indicates that is successful creation of your linear regression. So these are some parameters that is by default that it goes inside to this. And now if you just remember, we have some techniques. So each of the variables, what you basically do is, if you want to estimate each of the variables, or now since we have 16 different columns, that means you have 16 different coefficients. That is, all these coefficients are independent of each other, neither of them have some dependency among each other. So you can basically do a partial derivative like dou j by dou c or dou j by dou m with respect to each of the input attributes. So by that, what you basically get is, you basically get a coefficient. So in order to get coefficient in this case, you can write this particular statement. So it takes two things, that is idx stands for index, and for each column name you are doing an enumeration. So enumerate is just another method which is there. So this is the description of what the enumeration does. So based upon the training dot columns, whatever columns which you have in the X dataset, it will basically do this formatting. So when this, what it basically calculates, it calculates the coefficient value of each of the model parameters that you have. So if you just look at this particular syntax, this is more or less similar. We have discussed in the pandas operator. This is nothing but the replacement operator, the same thing. So there we have seen a use case. So majorly it is used in text to speech real-time application. To the same thing, we have some application when in model construction. So if you just run this, you can see that there are different values that you get. So what do you interpret from this particular values? So how this is read basically is, for each increase in the price. So let the unit of price be in any currency depending upon whatever country or whatever origin of that car model is. So for each increase in price, the symbolic decreases by these many units. For each increase in price, the wheelbase decreases by 8.89. For each increase in price, the length increases by 0.09. And so you do the same kind of relationship with all these different parameters that you have after pre-processing. So you can see some of the coefficients have a positive correlation, some of the coefficients have negative correlation. So that's how you estimate the coefficient for each of the input parameters that you have from your data frame. And now this is one way to check the model intercept. So like we have the equation y is equal to m1x1 plus m2x2 plus m3x3 plus up till m16x16 plus that c constant which is there at the end. So that is nothing but your model intercept. So in this sklearn library, you have a default syntax or way to write, that is model dot intercept and this underscore. So if you just go ahead and run this, you get an array. So it basically returns an array which is nothing but your intercept. So it is towards the negative axis in your plane. So this is internally calculated based upon all these given features and values, and this is the model coefficient that you get. So these are the different coefficient values for all the different parameters which you have. So these are 1, 2, 3, 4, and 5 in numbers, and you have all these parameters. So that are basically the model coefficients for all these different things which you can see here. So now by these two things, what you basically do is you will just run the accuracy, or which basically gives the variance that is explained by your model. So to this I basically passed on the test set. So whenever when you train the linear regression model or any neural network model, on the fit method you basically pass the training set, and whenever you want to evaluate it on the unseen examples, you basically write model dot score, and to that basically I pass the test set, test x and test y. So if I just run this, I get this value, that is 0.8181. So that is nothing but 81%, around 81% accuracy that I get. But there are around some 19% uh, loss that is there in my model, because that is the variance that is not explained by my model. So what this basically means, 81% of your accuracy or variation in your data is explained by your linear regression model that we have done so far. So there are even more pre-processing things or fine tuning or even the hyperparameter tuning especially we want to do, so that we can get more of the accuracy, or we can do the more statistics also in order to leverage this accuracy score. So there are around 19% approximately of the accuracy which is not fitting into this. So that is, or that my model can't explain. So this is how you build a model and basically you evaluate its accuracy. And this is a small meme. So that was all regarding the linear regression model in machine learning. So we have used some of the concepts from the pandas, NumPy, grouping, summarization, and some missing value treatment. So this is just for a dummy data set that we already have. So hope you guys enjoyed this video. If you found it educative this video, please do like, share, comment, and if you are new to this channel, please consider subscribing. Thank you very much for watching this video.